Hey everyone, thanks for tuning in today to this video where we're going to talk about approximating areas with Riemann sums. So let's go back to where we ended in topic 6.1. This is the same problem that we ended with in our video from topic 6.1. A particle Q moving along a straight path. The velocity, sorry, they kind of covered up there a little bit. Velocity and time. The graph of the velocity of particle Q at time t is shown to the, well, not to the left really, but below here. The equation of the velocity of particle Q be modeled by that function, 0.5 t squared plus 1. What is the total distance of the particle traveled from t equals 0 to t equals 2 seconds? And what we said at the end of topic 6.1 is that we want to find this area here. That's not possible. Using what we currently know, the knowledge we currently have, it is not possible, okay? So, although there are many possible techniques to approximate the area of the curve, we are going to use rectangles, and we call these Riemann sums, or trapezoids, which we'll talk about later on in AP Calculus. So we're going to start with rectangles. When using rectangles to approximate the area of the curve, we must decide a few things in advance. One, how many rectangles are we going to use? These are called subintervals. And two, how we would determine the height of each rectangle. We have three options for that: left point, endpoints, midpoints, or right endpoints. So let's take a look at our first approximation. The first one says, use the left Riemann sum with one subinterval to approximate the area between the curve. Okay? So to find the length of each subinterval, what you're going to do is you're going to take your ending point minus your starting point and divide it by how many subintervals you have. And that's going to be the length of each rectangle. So each rectangle here is going to be 2 units long. The height, we're going to use the leftmost height of the rectangle. So the rectangle is going to be this length. And how do we know the height of it? It's going to be the leftmost height of that rectangle, which is this height. That's the leftmost height that we see there. So now that we draw a rectangle, we estimate this area. Right? Our area is going to be, so we call A sub L for left. The base, the length is 2. The height is 1. So 2 times 1. Our area is approximately 2. Now looking at this, it's pretty obvious the area is not 2. Look at all this area we missed. Not only is it obvious it's not 2, it's obvious the answer is definitely higher than 2. All right? Let's take a look at another one here. This one says use a left Riemann sum with 2 subintervals of equal length to approximate the area between the curve. So now we got 2 subintervals. So endpoint minus start point over 2. Each subinterval is going to be 1 unit long this time. So rectangle 1, rectangle 2. And again, how do we know which height to use? Left again. So for each rectangle, we're going to take the leftmost height. So for this red rectangle, this is the most left height. So this is the rectangle we'll find there. And for the blue rectangle, this is the height. So this is the rectangle we'll find there. So those are the 2 areas we're going to find that add these together and see what we get. For the first rectangle, the length is 1 and the height is 1. So 1 times 1. For the second rectangle, the length is 1. The height might not be easy to know that right away. So what you do is just put this t value into your equation, and we get 0.5 times 1 plus 1. So 0.5 plus 1, or 3/2. So our approximation here is going to be 1 plus 3/2. Or 5/2, or 2.5. So now we're saying that the area is 2.5. But again, the area is not 2.5. Look at all this area that we're missing, we're leaving out. So again, we can say that the area is bigger than 2.5. Let's take a look at another one. Use a right Riemann sum with two subintervals of equal length to approximate the area between the curve and the x-axis from 0 to 2. So once again, we have endpoint minus start point over how many subintervals we're using, and that gives us 2 over 2, or 1. So each rectangle will again be 1 unit long. So our first rectangle, we'll go a red and blue one again. So there's our first rectangle, and there's our second rectangle, 1 unit long each time. But this time we are going to use the right heights. So for the first one, the rightmost height is right here. So there's our first rectangle. For the second one, our rightmost height is here. And there's our second rectangle. All right, so now let's find the area of these two. So area of the right. The first rectangle's length is 1. The height is the same height that we thought of for the second rectangle last time, which is 3/2. Again, we get that by putting 1 into our equation here. Plus, the length of the second one is also 1. Its height is 3. And if we don't know that exactly, all we got to do is put 2 into this equation. And that would give us 3. So our area is going to be 3/2 plus 3, which is 3/2 plus 6/2, or 9 over 2. Is our area 9 over 2? No, it is not. Look at all this extra area we added in. Okay, but what we can say about this so far is that we know the actual area under this curve is bigger than 5/2, but smaller than 9/2. Okay, so a good guess might be 7/2. Okay, that's definitely not going to be the answer, but it's probably pretty close to that. And we know it's between these two numbers because this one was too small, this one was too big. So a thinking question here, what would happen if we approximated area if we were going to use more rectangles, like 6 rectangles or 10 or 1,000 rectangles, which would be a not really fun problem to do, right? But what would happen? We'd probably be getting a better and better approximation with the more rectangles that we try. Okay, so if we tried 10 rectangles, our approximate area would be closer to the actual area. If we tried 1,000 rectangles, it'd be really close to the actual area. Example 4, Tiffany posts a picture of her posing with Sir Isaac from the pop group Sir Isaac and the Newtones that we talked about in our last video on our Instagram at 9 a.m. The rate that her followers view her picture is modeled with selected values shown in the table above where t equals 0 represents 9 a.m. And the rate is measured in people per hour. Use the data in the table to approximate the following. Okay, so the first one says write an expression that represents the area between p prime of t and the t-axis from t equals 0 to t equals 5, including units of measure. Okay, oh, sorry, I'm reading the second part there with units of measure. We're just going to write an expression first. All right, so our expression here is going to be an integral from 0 to 5 of p prime of t dt. Okay, that expression right there represents the area between p prime and the t-axis from 0 to 5, of course. B, use a right Riemann sum. So the key there is that it says right Riemann sum with 3 subintervals to approximate the area between p prime t and the t-axis from t equals 0 to t equals 5. Include units of measure with your answer. All right, so we're going from 0 to 5. All right, we're going to use 3 subintervals. So look at the table here. This is going to be 1, 2, 3 rectangles. So the first rectangle, the base is 2 units long from 0 to 2. The height, so how do we know which height to use? Is it 41 or 30? And that's where this word comes into play. Since it says right, we're going to use the right height, which is 30. The second rectangle, the base is from 2 to 4, also 2. And we're going to use the rightmost height, which is 54. The third rectangle, its height is 1. And the rightmost height is 26. So adding those together, we should get 194 people would be our units. So Tiffany's post will be seen by 194 of her followers between 9 and 2 a.m. And again, that's just an approximation because we're using a Riemann sum. All right. So question C, what does this answer represent in the context of the problem? I kind of just said that out loud, but I'll say it again. Tiffany's posts will be seen by 194 followers between 9 a.m. and 2 p.m. That's 5 hours after 9 a.m. All right, question 5, same problem, same table, but now we're going to use a left Riemann sum with 4 subintervals to approximate the area between P prime from t equals 4 to t equals 12. So 4 subintervals, 1, 2, 3, 4. Those are your 4 rectangles. Leftmost heights. So our area approximated by a left Riemann sum, and we should have put the right Riemann sum here. And again, these are approximations. The first rectangle has a length of 1 and a height of 54, because that's the left height of that rectangle. The second rectangle has a length of 1 and a height of 26. The third rectangle has a length of 3 and a height of 21. And the fourth rectangle has a length of 3 and a height of 44. Okay, add all those together and we should get 275 people. Okay, and we're again asked to interpret this. So I'm just going to do a little copy and paste here. Tiffany's post will be seen by 275 followers between the hours of 1 p.m., which is 4 hours after 9, and 9 p.m., which is 12 hours after 9 a.m. Example 6, same problem. Use a midpoint Riemann sum with 3 subintervals to approximate the area between P prime and the t-axis from 0 to 12. All right, so 3 subintervals. 1, 2, 3. Those are our 3 rectangles there. So area, midpoint, approximation. The first rectangle has a length of 4. How do we know what height to use? There's 3 of them there. It's a midpoint one, so we're going to use the middle height, which is 30. The second rectangle has length 2. And the middle height would be 26. And the third rectangle has length 6 and height 44. Adding they up, we should get 436 people. So, interpreting that one more time, Tiffany's post will be seen by 436 followers between 9 a.m. and 9 p.m. And again, these are just estimates. They're not perfect. These are our best guesses that we can come up with. So those are called Riemann sums. More often than not, those problems will be occurring on table problems like these last 2. Usually on the AP test, you won't see any problems like this. It's more out of these types of problems. All right, so the next thing and last thing for this topic today is the trapezoidal rule. So it's the same thing as Riemann sums with one exception. Riemann sums uses rectangles. The trapezoidal rule uses trapezoids. As we've been seeing throughout this topic, there are several ways of approximating using integral using geometric shapes. The trapezoid is another popular shape that is used. So the trapezoidal rule says that f be continuous in A to B. The trapezoidal rule for approximating the area in a curve is given by this here. Okay? So yes, that is a rule. Yes, you can memorize it, and yes, that'll work every single time. Or you can simply just split up each trapezoid one at a time. Okay? So I'll kind of show you both methods here, and you can pick and choose what you like to do. All right, so b minus a over 2n, that first part there, b minus a over 2n, where does that come from? Well, that comes from the trapezoid formula. So the area of a trapezoid formula, which we have written down over there, is 1/2 times height times base 1 plus base 2. That's the area of a trapezoid formula. So b minus a over n is the same thing as 1/2 times b minus a over n. So 1/2 is 1/2, and b minus a over n is your height of each trapezoid. And then these are all the bases. So example 7 says use the trapezoidal rule to approximate the area under sine of x and above the x-axis on the interval 0 to pi using 4 trapezoids. All right, so 4 trapezoids. We're going to do b minus a over 2n. So it would be pi over 8. So b minus a over 2n is pi over 8. So our area using trapezoids is going to be pi over 8 times. So then we have all these other things. Basically what you need to know is that the first height there's one of, the last height there's one of, and every height in between there's 2 of. Okay? So if we're using 4 trapezoids, 1, 2, 3, 4, right? So this is a height, this is a height, this is a height, this is a height, and this is a height. This height is only used once. It's in use this trapezoid here. This height is only used once in this trapezoid here. But the 3 middle heights are used twice. One in the trapezoid to the left of it, one in the trapezoid to the right of it. All right, so really what we're doing here is we're drawing what's supposed to be 4 trapezoids, but it actually ends up being only 2 trapezoids and 2 triangles. But that's not really something that's important for us to know right now. All we need to know right now is that we're using trapezoidal rule, and we have to apply that formula. So the first height is 0. There's only one of those. Plus 2. The second height, so it's right here, would be the sine of pi over 4. Okay, the sine of pi over 4 is root 2 over 2. The third height is the sine of pi over 2, which is 1. The fourth height, the sine of 3 pi over 4, which is also root 2 over 2. And then one of the last heights, because it's only in one trapezoid, is also 0. And that's it. Now we just simplify. So 0 plus root 2 plus 4 plus root 2 I misread my writing. This is not a 2, that's a 1. Really bad handwriting there. So this is supposed to be a 2. All right, again, just simplifying. We get pi over 8 times 2 plus 2 root 2. And if you want to simplify a little bit more, if we factor it out of 2, we get pi over 4 times 1 plus root 2. So that's our approximate area. Okay. Now, again, instead of doing the actual rule, memorizing this rule, you could simply do the 4 shapes one at a time. Triangle, trapezoid, 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 one at a time. And that will work. Let's bring us to our last problem here. The following table shows the speed in miles per hour of a cyclist at various times. Use the trapezoidal approximation to find the distance in miles the cyclist travels in a 12-minute time interval. Okay. So using our trapezoidal rule here, first thing we should probably figure out is b minus a over n. So that's going to be 12 minus 0, right? So 12 minus 0 over 2n. So what is n here? We're going to have, how many trapezoids are we going to have? 1, 2, 3, 4, 5, 6. So again, 1, 2, 3, 4, 5, 6. We should have 6 trapezoids here. Okay, so that would be 12 over 12, which is supposed to be 1. Okay, but to do this, I would actually encourage this the other way that we talked about, not to use trapezoidal rule here, but instead just do trapezoids one at a time. And when it comes to table problems, I would always encourage you to do that. Table problems just seem to be a little bit easier to do using individual trapezoids to me. That's just my opinion. Because usually each height is not going to be separated by the same amount. As you can see here, 2, 3, 1, 3, 1, 2. Different numbers each time. So if I was doing this problem, I would just do each trapezoid one at a time. For example, this trapezoid first would be 1/2. The base would be 2 minus 0. Sorry, the height would be 2 minus 0, so 2, times base 1 plus base 2. All right, so that's the first trapezoid. The second trapezoid, 1/2. The height would be 5 minus 2, so 3, times 25 plus 27. Third trapezoid, 1/2. The height would be 6 minus 5, so 1, times 27 plus 13. Plus the fourth trapezoid, 1/2. The height is 9 minus 6, so 3, and then base plus base. Fifth trapezoid, 1/2. 10 minus 9 is 1, and then base plus base. And finally, our last trapezoid, 1/2. 12 minus 10 is 2, and then base plus base. And as you can see here, it is pretty much the same thing as the formula. We use the first base once, the last base once, right? And then all other bases, 25, 27, 13, and 21, all get used 2 times. Okay, so we can use our calculator to figure out what this number would be. It ended up being 234. So what does this mean here? Okay, we want to think about what does this number actually mean here. So the speed is in miles per hour, the time is in minutes. So we're talking about 2 different numbers here, two different labels, 2 different units. So we got to figure out what that would be here. So it's 234 miles in 1 hour, and 1 hour is 60 minutes. So 234 miles in 1 hour, and 1 hour is 60 minutes. Okay? And then just multiplying by the time, which is minutes, which we've already kind of taken care of that. The actual number, which we kind of already figured in the first place, is 234 over 60, which is 3.9 miles. So it also would have been possible to convert the times in the table to hours prior to doing all this, but then we'd be doing, 7 different conversions instead of just the one conversion at the end. All right, quick note there on the side, the distance between your given values of t do not have to be equal. This is true in computing with a rectangular Riemann sum as well. And when that's the case, that's definitely what I would say to use individual trapezoids or individual rectangles instead of doing a formula that we learned today. Okay, and then a little tip there on the bottom on the AP exam, it's very important that you show a sum of products whenever you are constructing an approximation of area using either Riemann sums or trapezoidal sums. In other words, don't perform any arithmetic calculation in your first step. Basically, this would need to be there. That's going to be 1 point usually on the AP test. Just showing all that out is 1 point. All right, even if it's a calculator problem and you're doing that in your calculator, doing your head, you can't just write this down. This all needs to be there to get credit for that. Okay, that will do it for our notes today on approximating areas with Riemann sums. Hope you enjoyed it. Hope you learned something. Thanks again for checking out this video.